Welcome back, Trig fans. We're going to look at trig limits and derivatives. We are going to look at the primary trig derivatives. This is part 1 today. So let's get going. And may I just say, don't try this at home. And the reason I chose this is because obviously as the wheel of the scooter spins faster, it creates a faster spin of the merry-go-round. And of course, the faster we spin, the faster the angles at which we spin are changing, which would warrant an interesting questions about the angular velocity. And that's what trig derivatives are all about. So let's get started. Excuse me. Okay, so to warm up, we need to start with what we know. So here's a function, and what I'd like you to do is draw the derivative of this graph. So where is the slope of this sucker? 0? Where is it positive? Where is it negative? So take a moment, pause the video, and sketch it. Okay, so here's what it looks like. So you have this blue guy right here, and we know that the slope right there is 0. That's why it's 0 right there. And we can see right there that the slope is 0, so that's why it has an x-intercept there. And, oh, excuse me, the slope right here is 0, and the slope of this red guy right here, the slope is 0. So that's why the x-intercepts are where they are. There's a slope of 0. Excuse me, there's a slope of 0 right there. Notice that up until this point right here, it's a negative slope, and so that's why the derivative is down here. Notice in between this guy and this guy, the slope is increasing. That's why this is positive to here. And if we continue around, this is 0, and then it's negative, and then it's 0 again, and that's why the slope from here to here is negative. And then, of course, beyond that, it's positive. So if you need any more time with that, I encourage you to, well, I'll give it another go here. Just to be clear here, can you see that right here the slope is approximately 1? Well, if we go up there, that's approximately 1. And here it looks to be maybe more than 1, so it's going to go up until we get to this point. Okay, so that's how we see it. So what I want you to do is draw a sine wave on your desk, and what I want you to do is sketch the derivative of the sine wave. That's the task. So pause the video and give it a go. Alrighty, so what I'm going to do is demonstrate. You probably have a good idea of what the derivative might be. Well, I'm going to take each point. So the slope of that blue guy we can see is positive 1, and the slope of the red is 0, and the slope of the black slope would be negative 1, and the slope of the orange slope is 0, and the slope of the green slope is positive 1. And if I drew a quick little curve in between there and then graphed it, do you notice anything? This purple line represents the derivative of the red guy. And if you look carefully, we'll see that that's actually the cosine wave. So we're suggesting that the derivative of sine x is cos x. What I'm going to do now is provide an algebraic proof. And here we go. So, I'm also going to now get you to graph the derivative of cos x. And if you follow the same process, you will determine that the slope is not sine x, but negative sine x. What I'm now going to do is do a proof for the derivative of sine x being cos x. So here we go. Alrighty, so first off, we're going to start with Newton's quotient. And there it is, and we know Newton's quotient well. Let's just show it to you one more time so we can just see that as h gets closer and closer and closer and closer and closer, we can determine the slope at one singular point. And that is the beauty of the derivative. And so that's what we're going to do here, and I'm going to demonstrate that with you right now. Okay, so a couple things to think about is we do need our addition identities. These are going to be important to this proof. All right, so first things first, here's Newton's quotient. So we're going to fill it out. Here's the sine x plus h, and here's sine x. Of course, this is y2, y1, and this is the change in y over the change in x's. And remember, this is h because it's x plus h on the bottom. Subtract x, and the x's would cancel out, leaving us with h. Now, do you notice that this is of the form sine a plus b? So we're going to use this identity, which we proved, and we're going to fill this sucker out. So there we go. Sine x cos h plus cos x sine h minus sine x over h. Now, it doesn't look like much right now, but there's kind of a cute little move here. And that is, I'm going to let h go to 0 in some places. And remember, so that we have the cosine of h. So if we have the cosine of 0, we know that on the cosine wave that when cosine is 0, we're at a value of 1. So that's really important. So the cosine of 0 is 1. And remember, it doesn't matter when we let h go to 0. Because it's going to go to 0 anyway. So we're conveniently choosing a time to do it, and that's what we did. Now what I want you to do is look at this. Do you notice that anything here will cancel? I think you do. I think you can see that sine x minus sine x is 0. And now we're left with this guy. Now I'm going to rewrite it just slightly. I'm going to go the limit of h as h goes to 0 of cos x multiplied by sine h over h. Okay, so as h goes to 0, what's the value of sine h over h? In order to answer that, you need to go back to our first lesson of trig limits. What is the value of sine h over h as h goes to 0? Well, we know that as h goes to 0, sine h over h goes to 1, which means that we've shown that the derivative of sine x is cos x. So we've done it. There we go. We've algebraically proved it. Now, some other things that I'd like to just do a quick reminder of. Let's see if I just want to make sure I have the most up-to-date slides here. So I'm just going to refresh this. And here we go. So what I want to do is just do a quick reminder. You should know what the derivative of f times g is. And this is our product rule, so fg plus fg prime. You also should know the quotient rule, which is f prime g minus fg prime over g squared, and you should also know the chain rule. So if this is f of g or f of g of x, that would leave us with, excuse me, f prime of g times g prime. Okay, so let's just look at that before we get into the trig stuff. Let's just make sure. So I think if we asked you to find the derivative of that, you know that the 7 comes down to the power 6, and then we multiply it by the 5. That's why we call it the chain rule. And the 7 comes down to the power of 6, and then the derivative of 5x plus 2 is 5, and we'd simplify it from there to make it 35 bracket blah, blah, blah. Now, same thing here. We'd end up turning that to 5x plus 2 to the power of 1/2. We bring down the 1/2, subtracting 1 from that, and then again multiplying by 5. So what would the derivative of sine 5x be? Well, a lot of people are going to say cos 5x, which is partially true. Don't forget the chain rule. There's the missing 5 right there. Okay, and this one here, the cosine of 5x squared, what would the derivative of that be? Well, we just learned that the derivative of cos A is negative sine A, and so that's why we're going to see the negative sine 5x squared, and then the derivative of 5x squared is 10x. Okay, now, what I want to do, just before I set you off on your own here, to try the challenges on your own or with a partner, would be to just make sure you saw a more complicated version, okay? So if we said, what's the derivative of this? First off, note that this 4 up here could also have been placed right here. So it would have read sine to the 4th power of 5x to the power of 3, okay? But I chose to do it there, and that's where it is. So when I take the first piece of it, we know that this is of the form 10a to the power 4, and the derivative of 10a to the power 4 is 10 times 4a cubed. I think you'd all agree with that, and that's what it would look like. There's my 4, there's the a function to the power of 3. Now remember, this is the chain rule. We haven't taken the derivative yet of this guy here, so the derivative of sine b would be cos b. So that's why we have cos 5x cubed. Now we're not done yet. This is the chain rule. We haven't taken the derivative of that piece, and the derivative of that piece would be, of course, the derivative of 5x cubed is 15x squared. And so there you go. So it would be this green piece plus this blue piece plus this red piece. And when we put it all together, it would look something like this. And when we simplify it, we take that 15 times the 4 times the 10 for 600. The x squared would come to the front. And we could leave it like so. Notice we could use a sine double angle identity, but we'll look at that later. Just be thinking about that, but I chose not to do it here. We'll take a look at that in time. So here are your challenges. I encourage you to stop the video before I speak. And anything in red for the most part are warm-ups. So if you could, this is one we've done before, so you may or may not need to do that. Okay. So I think you're comfortable with that. The 4 would come down to the power of 3, and then the derivative of that. So I'm not going to spend too much time there. Excuse me. Now the derivative of this guy, of course, you're going to take the time to do this, so pause the video. And of course, what we're going to do is the derivative of sine is cos 9x minus 71, and then the derivative of 9x minus 71 is 9, and that's how we would leave our answer with the coefficient in front. Let's look at one that's a bit more complicated. This one is more tricky, or you might not know what to do with that too. So first suggestion would be to put it out there, and now we're just going to use the chain rule. So the 2 will come down. So the 2 comes down, cos x to the power 1, and then we need to take the derivative of that internal piece, which is negative sine x. Now, notice this. This is a sine double angle identity. Can you see it? So we could leave this as a negative sine 2x. So be looking for that. That'll show up a few times. Let's look at challenge 2. Okay, so this one's a little bit more complicated. So give it a go. And let's take a look. Okay, so what happened here is we took the 3 up, and then we took the derivative of something to the power 3. So the 3 came down, leaving us with cos squared 11x. Then we took the derivative of cos 11x, which is negative sine 11x, and then we took the derivative of 11x, which is 11. So you might want to play that video back so you can hear the playback there, but all I did was use the derivative and the chain rule derivative. Okay, let's look at this one. This one is definitely more complicated, very complicated. So again, take your time. There's a lot of chains here. So there's the answer. And here's how we got there. So the first step would be to bring the 5 down, as you can see, and then everything else inside. So this is 5a to the power 4. Now we consider what's the derivative of a, the part inside. Well, the derivative of 1 is 0, and the derivative of this guy is really going to be 3b squared. So the 2 will come down for 6, and it'll be 6b to the power of 1. Well, we're still not done yet. We need to take the derivative of sine x to the power of 7. So you can see here that the derivative of sine c would be cos c, and then the derivative of x to the power of 7 is 7x to the power of 6. So then when we rearrange that, notice the 7 will come forward with the 6 and giving us 210x to the power 6. Notice that we have sine x to the power 7, cos x to the power 7 multiplied by that. Do you notice that this again is of the form sine 2x? So what we can do is use the sine double angle identity, and when we do that, we're going to get sine 2 times x to the power 7. So again, notice that this would have been 2 times 105. So 2 sine x7 cos x7 turns into sine 2x to the 7. So please look for that. All right, let's look at challenge 3. So challenge 3 says if you already know how to apply the product rule there, then this would be optional. Okay, so I'm going to trust that you're okay with that. And that's why my explanation here will be brief. So the derivative of 5x plus 1 is 5 multiplied by g plus the derivative of this guy, which is going to be 5x minus 1 to the power 4 multiplied by the original function. And then what you can do is you can factor out some x minus you can factor out some x minus 1s, and when you do that, that is what you are left with. So let's take a look at the trig version, and I'll get you to give this a go right now. Press pause on the video and give it a try. Alrighty, so remember, this is going to be the derivative of x cubed is 3x squared times g plus the first function. There's my f, and then the derivative of sine 4x is cos 4x, and don't forget to multiply it by the 4. we could factor out an x squared, and that looks like about all we could do there. So there it is in its finished state. Let's take a look at challenge 4. We're going to be looking at the quotient rule, and again, we'd be using this quotient rule right here, and when you do that, you get this. So we're going to trust that you know how to apply the quotient rule. We'll walk through this one together though. So the derivative of x squared is 2x times g plus f times the derivative of cos x is negative sine x. Remember, that's why that's a plus, because it was subtract negative sine x. So it's positive. There's a couple of ways we could leave it. We could leave our answer like that. We could also see that, we could see that cos x is, we could simplify here and here. So if we do that, cos x over cos squared x is secant x, and sine x over, cos squared x is secant x tan x. And of course, if we did that, we could also factor out a secant, an x and a secant, looking like that. But all three of these would be accepted. Okay, and let's take a look at these last two. This is tricky again, so pause the video, give it a try, and here we go. Okay, so just to be careful here, this is not the product rule. This is the cos of sine x. So you want that 2 up there before you do anything, and wrestle with it and come see us if you need any help. But here we go. So the 2 came down, leaving us with, and I think this is too hard for me to explain without the steps in the middle here. So again, just remember that you put brackets around this and put the 2 out there, and it's going to be the cos of sine x. The cos of sine x. And so wrestle with that. Let us know if you need any help with that one. Let's take a peek at this guy. And did I put steps in there? I think we're past giving you steps. So this is just wrestle time. So take your time on these. The key thing to notice here, you notice that this guy and this guy are of the sine double angle identity. And that's not necessarily easy to see. Cos of sine x, sine of sine x. So it's a bit of a weird one, but this is now going to be the sine of 2 sine x bracket. And those cos x's are always there. Okay, so that's 2 cos sine, which is our double angle identity. And notice that also happened right here. This is sine a cos a, which is this identity right here. Excuse me. And there we go. So friends, I trust that you are making entries into your digital portfolio after each class, and at a minimum 2 to 3 times per week. So you had an opportunity here to connect trig derivatives with the other derivatives that you know, and you also were spending some time with your partners, I hope, connecting and wrapping your minds around these big ideas. Okay, so we're going to end this. Make sure you try the questions in the notes, and these would be key questions to try in your practice.